All right, here we go. Making some lectures. It's Sunday afternoon. I'm probably around like day 6 or so of this coronavirus. To be honest, not too bad. Some mild cold, fever here and there, some chills and stuff. You know, a little tight chest on occasions, but other than that, not too bad. The wife is doing fine. Kids, I think, obviously have it at this point, but are not showing any symptoms or anything. We did have them tested, but I haven't got any results back yet. But anyways, things are going fine. Hopefully it continues to go that way. Knock on wood, right? This is what I get for being optimistic. How dare I do that, right? I still can't believe that happened. And I was all excited about life last Monday. And then boom, 2020 puts me down. Here, fine, take COVID. So, anyways, pretty sure we got it from going out to eat. Went out to eat with some friends, first time in 7 months. I think I mentioned before. They recently came down with it shortly after us, so I think we were both exposed at that meal. So it was either our other friends that were there with us or something else at the restaurant that got us. So, anyways, things are going well. I want you to keep working on that homework, that seismic homework that you guys were working on before, right? That thing is due this coming Friday, right? Hopefully you started that thing early. I'll be available this week for questions and concerns and stuff like that on your modeling and whatnot. But hit it hard. We are going to start a new topic. It's the last topic that we're going to cover. It's multiple degree of freedom systems. Right? This is one of the topics that I really enjoy teaching. Right, the seismic code. It's interesting, right? It really ties back to the. I really enjoy that aspect of it. What we just covered, right? The single degree of freedom systems. We worked our way up to response spectra, and then we talked about how that ties into the code, and then we dive deep into the code and kind of go through all the key components in the code, right? My heart though is in the theory of stuff, the response spectra, coming up with that, and then doing the coding and all that. So I like to we're coming back to that realm now when we're coming back to the multiple degree, for instance. I know some of you like that, right? Some of you prefer the code, but get ready for a little bit of a ride here, because multiple degree of freedom systems, right? We're going to have some matrices and vectors and eigenvalues and things like that. And so some coding coming up. So, but also a really cool math concept that really actually captures what happens in the real world. So again, this is a pretty neat subject, multiple degree of freedom systems. So what are multiple degree of freedom systems, right? Well, you have multiple degrees of freedom, right? You have multiple masses, multiple degrees of freedom, right? A perfect example, this is usually what we start out with, is this mass spring damper system, right? These things should probably be on rollers, right? Because they're not suspended out there. So, but the point is, you have a lump mass and a lump mass, and they're attached to each other, okay, via a spring, and then there could even be a damper in here. We're going to start out without the damper, but you can imagine there could be some dampers in there as well, and they have applied forces on it. And where things get a little complicated, right? This is more than just like coming up with you can't just come up with like an effective stiffness between the two. It can't just be the 1 over K1, the 1 over K1 plus 1 over K2, that being the total stiffness, because now we actually care about how does this point move relative to this point. Whereas when we had before, when we formulated this, it was like a spring and then another spring, and our mass was here on the end, and we only cared about what the mass was here on the end. We didn't really care about what was happening at this point. Now there's a lump mass here, and we care about what's happening at either end. So that's what's happening. You can see how this stuff gets complicated, right? Is because what's happening at M2, right? If M2 moves back and forth, right? This spring gets stretched out, and M2 moves to the right or M2 moves to the left. It's going to affect what's happening at U1, right? Because they're attached by this spring K2, right? So if I move M2 to the left, well then K2 is going to push on mass 1, right? And it's going to affect how mass 1 moves, right? And then vice versa, if I move M1 to the right, it's going to move M2, right? Or if I move M1 to the left, it's going to pull on M2. And so you can imagine that what's happening over at this one is affecting what's happening over here, right? And they're linked together by this spring, right? And you can imagine, right, what we're going to be trying to do is, it's kind of hard to gesture, actually possible gesture, that's what I'm trying to do with this pen, but both of these things are going to be moving, back and forth, and they're going to be affecting each other, okay? Well, how do we go about modeling that? How do we account for that, those displacements, right? Or how do we model that behavior as it's oscillating, okay? This is equivalent, this system right here is equivalent to this system here, right? We've got stiffnesses this is a shear frame building. You got stiffnesses from the first floor, and you have stiffnesses for the second floor, and you have your masses lumped on the different floors as you go up. And you can imagine if I pull the top of this building back and I let go of it, it's going to be affecting what's happening to the second or to the first floor, right? It's going to kind of swing back and forth, and it's going to affect what's happening to mass 1, and mass 2 is going to be affected, or mass 1 is going to be affecting what's happening at mass 2, because they're attached to each other by this spring, essentially, right? By this by the columns, which are essentially the same as these springs right here. So anyways, you get the point. You have multiple degrees. In this case, we have, right, the top floor moving relative to the first floor, and the first floor affecting what's happening at the second floor, and so on, right? And you have the lump masses there. So these guys are equivalent to each other. Now, how do we go about capturing all of this? So the first thing you do is, let's just come up with, let's look at the free body diagram of each of these masses, right? And just keep in mind, we're going to do it for the spring mass damper system over here, and not this, but you can imagine these things are the same, right? You could come up with the same free body diagrams and stuff for the different systems. The results will be the same. And so what I'm going to do is I'm going to say, okay, if I took this thing here and I move it to the right a little bit, what are the forces going to be on this guy right here? Okay, and so what we got, let's draw what those forces are going to be. We've got a force going this way on that mass. Oh my gosh. I changed my operating system on this thing. It's driving me nuts. We've got K1 times U1. And then this direction, we've got that load P that's applied to this thing. And then we also have the reaction from the other spring on the other side, and that's going to be K2 times the relative distance between them, K2 times U2 minus U1, right? That's how much that spring is going to be stretched. How much K2 is going to be stretched is going to be U2 minus U1, right? That'll give us how much that thing actually gets stretched. So that's what that is. K2 is plus K2, U2 minus U1, right there, okay? And we look at the forces acting on mass 2, it's going to be equal and opposite. You're going to have, like this is going to be K2 times U2 minus U1. And then we're going to have P2 on this side. All right. Those are the forces that are acting on those different masses, right? This is going to be this is going to be equal and opposite of this, right? And again, it's just that K2 stiffness. Nope, I'm not gonna like that. U1. Okay, so K2 stiffness multiplied by the difference in between the displacements. Okay, so that is what our free body diagrams are. Now we could draw the equations of motion. I'll write the equations of motion. For mass 1, the equation of motion is going to be positive P1 plus K2 times U2 minus U1 minus K1 times U1. And that's equal to mass times acceleration, right? U1 double dot. right? Because these forces are going to be affecting the acceleration of mass 1, right, which is mu1 double dot. Okay, so that's the equation. That's the equation of motion for this mass, and so let's write equation of motion for that mass. So now we got P2 minus K2 times U2 minus U1 is equal to M2 U2 double dot. So this should be a M1 up here. M2 U2 double dot down here. So this should be a 1 here. I forgot to put that there before. And that's M2 U2 double dot. Okay? So those are my two equations of motion. Right? These two forces will affect the acceleration of mass 2. All right? So you can see what this is. This is a type in here. What's going on? What's going on, buddy? Okay. This is a system of differential system of differential equations. Right? This to solve traditionally and solve them numerically. We are solved with modal analysis. Right? And we'll come back to that. I guess that's what today's lecture is all about, is what this modal analysis is. But the point here is that it's a system of differential equations. Why is it considered a system? So it's a system of second order, linear, non-homogeneous differential equations. Okay, linear because there's no u terms multiplied by each other. Non-homogeneous because if you rearrange this to put all of your u's on one side, you'd have, though it'd be equal to two constants, and so that makes it non-homogeneous. It would not be equal to 0, would make it non-homogeneous. If these guys are 0, then it would be homogeneous. Second order because you count the number of dots. There's 2 dots there. Okay, but the reason it's a system is because what's happening, right? So what you're after is what, right? When you try to solve these differential equations, what you're after is the equation. What the equation u1 is going to be, right? That's what you're after, is what u1 is a function of time. So you find u1 such that the second derivative multiplied by the mass is equal to all of this stuff over here, right? Well, the problem is what's happening at u1 is a function of what's happening at u2, right? We knew this was coming because, right, obviously what's happening over here is going to be what's happening over here is going to affect what's happening over here because they're attached by the spring. And so you can see that u2 over here. So if I'm solving for u1, it's a function of u2. Same thing down here. I'm solving for u2, okay, but it's a function of u1, right? So what's happening at u1 is affecting what's happening at u2 and vice versa, right? And so they're linked to each other. You can't just solve this one because I need to know what's happening at u2, and I can't just solve this one because I need to know what's happening at u1. And so they're coupled. Okay, and they're linked together. And so that's what makes it a system, is that you have both of these equations of motion are linked to each other. Okay, like I said before, how we're going to solve this, you could solve this thing numerically. There's methods to solve a system of differential equations numerically from the get-go. Okay, but we're not going to do it that way. We're going to solve this thing with modal analysis. Okay, and it's a classical method for solving these things. The code allows for modal analyses. That's why we're going to learn this method. Okay, it is, in my mind, a pretty sweet method. It's pretty cool what it comes out of this stuff. Okay, so the first thing we're going to do is we're going to start. These equations can be rewritten in matrix form. Okay, so that's what the first thing we're going to do is we're going to switch over and start using matrices. Okay, because again, you can rewrite this equation in matrix notation. It's a lot cleaner to do it in matrix notation. It's a lot slicker to do it that way. So we're going to do it that way, and it lends itself to doing it in modal analysis. Okay, so in matrix notation, okay, so what we're going to do is you define your mass matrix. Okay, and I'm going to try to be pretty religious. I'm going to put my square braces around my variables that are going to be matrices, and I'm going to put lines over my matrices or my vectors in my system. Okay, and so the notation I'm going to use. So my mass matrix I'm going to define like this. So I'm just going to lump it. You just put your mass 1 and your mass 2 in your diagonals like this. So I just look at this as mass 1 and mass 2. I just put them down the diagonals. There's certain cases where it's not, and I'm putting zeros in the off diagonal terms. There's certain cases where that does not stand. Okay, for now though, that's how we're going to do it. I'm going to put zeros in the off diagonals, and then our mass matrices or our masses on the diagonal like this. So that's what our mass matrix looks like. Okay, our acceleration matrix or our acceleration vector is just going to be acceleration of mass 1, acceleration of mass 2, and you just put them in a vector and you stack them on top of each other like this. Okay, K is our stiffness matrix. Okay, in this particular case, we end up with K1 plus K2 in the upper left, and then K2 in the bottom right, and then you got negative K2s in the off diagonal terms. In a minute here, we'll talk about how you go about assembling that matrix. Okay, how you go about assembling your stiffness matrix, but for just take it for what it is right now. That's what that stiffness matrix ends up being. Okay, K1 plus K2 up here, K2 down here, and then negative K2s in the off diagonal terms. So a little side note, these guys right here, these off diagonal terms, well, we'll come back to that. Okay, so that's what our stiffness matrix is. Okay, and this is just for a two degree of freedom system, right? So if you have a 2 degree of freedom system, then you have a 2 by 2 matrix here, and you have 2 accelerations, right? And you have 2 masses as well, right? If I have a 3 degree of freedom system, you can imagine that would have 3 terms in it. This would have 3 terms in it. This would be a 3 by 3. Okay, my displacements, just like my accelerations over here, I'm just going to stack them, U1 and U2, and then my loads, if you have them, right? We're going to do free vibration first in a few minutes, but you stack them like this, P1 and P2. Okay, so those are all like the matrix representations of the key components of this problem up here. Okay, so what I do is I just say, come down here, and this is what we write our acceleration, right? Mu double dot plus Ku is equal to P. That is just our standard equation of motion it's what we had for single degree of freedom systems. Now it's just you write the same thing in terms of matrices, and for multiple degree of freedom system, Mu double dot plus Ku is equal to that load, right? And so when you write it out in matrix notation, this is what it looks like. Okay, M1, M2, U1, right? So this is mass times acceleration right here. This is K times U, and that's equal to that load. And if you carried out this matrix math, what you get is these equations. Right? So these guys are equivalent to each other, right? And you could, if you wanted to show that to yourself, you could, but if you think about matrix math, what you do is you take these two guys and you kind of flip them on their sides and you multiply them by these guys and add them up. So you take this guy, multiply it by this, and then you add it on this guy multiplied by this, and then that gives you this term up here, right? And then you can see that gives you these terms when you do that. And then you come down to the next row, you take these two terms, you multiply it by these two guys and add them up. So this guy gets multiplied by this guy, and you add on to it this guy multiplied by that guy, and you can see that you get that term right there, right? And so that's all that this is doing. It's just a different way of writing this equation, right? But a little bit slicker because you've done it in matrix notation, okay? So this is equivalent to writing that, okay? So that's pretty nice. So then we come down and say, like I said before, how do you go about, like, where did this guy come from? Okay, and so the book spends quite a bit of time talking about assembling stiffness matrices and all the process involved and stuff like that. We're gonna keep it kind of simple in here. We're only gonna look at these shear frame type buildings. Okay, we're gonna look at this cases where you have, this guy moving and this guy moving, and how do you assemble the stiffness matrix. I think we'll go up as big as like a 4x4 at some point. Okay, but it quickly gets out of the realm of what you can handle. You can imagine if you have a system that's really complicated, we'll cover those different systems in a minute. It gets really difficult to assemble a stiffness matrix. That's what computers are for. They're really good at assembling stiffness matrices. But for the very basic way that you can assemble a stiffness matrix, especially for just simple systems like this or a shear frame. This is considered a shear frame if we have these things infinitely stiff, and then these guys modeled as 12EI over L cubed. Those are called shear frames. If you were to assemble a stiffness matrix like that, is this method. You can use this method right here. It is called, I'm thinking about this. I'm just debating here. Do I record a lecture or watch it live? Debating just giving this lecture live. Let's just try this. Let's try it this way with this pre-record lecture. I don't like it as much because you clearly might have questions. You can't ask them because you're not here. This works for dynamics because the stuff is a little bit easier, and this stuff is pretty heavy, pretty heavy. I'll just do this recorded lecture, and then we'll spend a little bit of time reviewing next time we meet live. Anyways, okay, sorry. So the way that you do this, the easiest way to solve this thing, okay, is what they actually call. Historically, they do call it this, and this comes up in coding quite a bit. But what they call this is master-slave method. But I don't know if you've seen this recently. So this comes up in coding a lot. There's a lot of things that come up in coding with master and slave. But in the coding world these days, they are moving away from master and slave, okay? Because of obvious reasons associated with racism and things like that. The coding industry has moved away from the terminology calling master and slave. And so we're going to call this move and react method. Okay, they both mean the same thing, but it's just a curious thing that's come up recently is that in the coding industry they're moving away from calling master and slave. I don't think there's any real negative connotations associated with it. I guess maybe some people are. There are still terms called masters and slaves, and that's something that's historically throughout all of history there's been slaves and masters and stuff like that. But anyways, we're moving away from that terminology, but. Which is fine. We can just call it move and react, okay? And so what we do is we think about this. We come up here and we look at this little right. This is a 3x3. This is going to be a 3x3 matrix down here, but it's a 3 degree of freedom system, okay? And what we do is we're going to do this. I'm going to define positive and negative like this. So if a force acts to the right, we're going to call this a negative, and if a force acts to the left, I'm going to call this thing positive. And this is a simple way of assembling a matrix. That's all we're using this for. Kind of talking about where this came from. And you may be called upon in the future to assemble a quick matrix. And so what we do is we're going to move this guy. We're going to think about moving this. Okay, and then we're going to see what it has an effect on. So on this side, it has an effect on this. Right? And you could do this for even more complicated degrees of freedom if you wanted to. We're just going to do it very simple for these guys where they can only move one direction. So if I move mass 1, what does it do to mass 1? Well, so what I do is I come down and I take this mass 1, and I'm going to take that mass, and I'm going to move it to the right. Okay, when I move it to the right, K1 will pull back to the left, and K2 will push to the left. Okay, and I said before, over here, if it goes to the left, we're going to consider that positive. So if I move M1 to the right, K1 and K2 push to the left. And so what I write here is K1 plus K2. Okay, so that's how it had an effect on mass 1. So now, if I move mass 1, what does it do to mass 2? So I take mass 1 and I move it to the right. What does it do to mass 2? Well, K2 will compress a little bit, and it'll push on mass 2 to the right, which is going to be a negative. And so what I write here is negative K2. Right? Because moving mass 1 affects mass 2 with K2 pushing to the right, which is a negative. And so put a negative K2 there. If I take mass 1 and I move it to the right, and U2 stays stays in place. Okay, so this guy stays in place, and this guy stays. How does moving mass 1 affect what's happening at mass 3? It does not, right? Because mass 2 doesn't move, and so when mass 1 moves to the right, it pushes on this thing. That's not moving, and so K3 never gets activated, and so it does nothing to mass 3, right? Then we come over to mass 2. If I move mass 2, what does it do to mass 1? If I take mass 2 and I move it to the right, like that guy, move it to the right, it's going to pull on mass 1, right? It's going to pull on the right to mass 1, which is a negative. So I'm going to write a negative K2 right there. Let me see that. If I take this and I move it to the right, it stretches this thing, which pulls to the right on mass 1. And so then we write a negative K2 there, because that's the effect that it has on mass 2. Mass 2, what does it do to mass 2? If I take mass 2 and I move it to the right, then the spring K2 gets stretched, and so it pulls to the left, and K3 gets compressed and it pushes to the left, and to the left is both positive, so this just becomes K2 plus K3. What does mass 2 do to mass 3? Moving mass 2 to the right will compress K3, which will push on M3 to the right, and so that's going to be pushing to the right, gives me a negative, so that's going to be negative K3. And so then you can imagine last one, mass 3 to mass 1 does nothing. Mass 3 to mass 2 does negative K3. And mass 3 to mass 3 does K3. Okay? So there, right, if I move 3 to the right, K3 gets stretched, and so it pulls to the left. Pull to the left is positive, so it's K3 down there. So that is our stiffness matrix. Okay? And like I said, this works for all systems, even really complicated systems, right? We're just doing, 3 mass spring systems. It would obviously work for this because these guys are equivalent, right? This guy and this guy are equivalent, so those things would be fine. But it also works, our next step, it works for a system like this. Okay, and it works for a system like this, and a system like this, and this, and this. So we'll talk about these systems later, but this is, as a structural engineer, this is the type of system you're going to deal with, where you have multiple degrees of freedom per node. You can really go through and assemble a stiffness matrix that same way using this master-slave, or the move and react is what we're going to start calling it then, okay? But for the most part, we're going to only have to generate stiffness matrices for simple systems like this. Okay, once you assemble that stiffness matrix, then it works in this system down below, where we define our mass matrix and our acceleration matrix and our displacement matrix like that. Okay, now things to note about this, right? These guys are all positive down the center. Right, those guys are all positive on this side. I think that worked. Terms are positive down diagonal. Those are key components of this. That's enough. Also, make sure terms down the diagonal. Off terms are what is coupling the system. How U1 affects U2. Okay. These off-diagonal terms right here, they also happen to be negative here. I don't know if they're always going to be negative. I have to think about that. I think in this case they would always be negative. Okay, but the biggest thing is this, right? This off diagonal terms, negative K3. This is where the coupling comes from. This is why when you have off diagonal terms, this is why what is happening at U1 is affecting what's happening at U2, right? Right? It's this, right? K2 is what's causing U2 to affect U1, right? I guess let's go to this 3 by 3, right? K3 is affecting what's happening between U3 and U2. K2 is what's affecting what's happening between U2 and U1. If you didn't have off diagonal terms, if you didn't have these terms right here, they would not. You would have an uncoupled system. What was happening at U1 wouldn't be affecting what's happening at U2. Would not be affecting what's happening at U3, right? Or in this here, you can see, right? I take U, when you do this matrix multiplication, do U1 times K1 plus K2, and I do U2 times that one right here, this negative K2. And if this wasn't here, then U2 would be multiplied by 0, and it doesn't affect what's happening in the grand scheme of things. This is going to play out because when we do this, when we do modal analysis, that's one of the things that we're going to try to do with this modal analysis is we're going to decouple the system, right? We're going to knock the off diagonal terms off. We're going to knock these guys off, these negative K2s and negative K3s in the off diagonal. We're going to knock them off of there, right? We're going to get rid of these guys. And so then it becomes an uncoupled system. We could solve it as 3 independent equations of motion and then bring it back into the real world. That's kind of the process that we're going to do. So I'm beating the horse to death and really pointing out that you have these off diagonal terms, and that's what's coupling the system, which is making what's happening at U1 affect what's happening at U2, what's happening at U3, and so on. Okay. If I were you, I would look through your textbook on this section, right? I'm really hand picking out. This is a really long section of the book. I'm really picking out the key components of it, but read through it. Right? It's all kind of neat stuff, and it'll help you understand what's happening globally. Okay, so there's assembling a stiffness matrix. There's just a different way of writing our equations of motion, right? Based off of this, we've talked about how we have these off diagonal terms that are causing the coupling of the system. Okay, the other types of systems I've mentioned before, right? The whole first part of your textbook, when it starts talking about multiple degree of freedom systems, the first part of that textbook talks about all sorts, right? Before they dive into the solutions or anything, it just talks about all these different equations of motion, different ways of setting up multiple degree of freedom systems. So there's a whole bunch of different systems out there. Right, you can define. I mean, a multiple degree of freedom system just means you can define a certain point by more than one displacement. So a system that looks like this, right? When this thing moves around and oscillates and stuff like that, you can define this end point as with a y direction and an x direction, right? The location of this point can be defined by those 2 points at all times. So that's a 2 degree of freedom system. It's kind of weird to look at it that way, but you could assemble a stiffness matrix and a mass matrix and stuff like that for this system as well. Okay, and you define your displacement of this whole thing based off of U2 and U1, right? And so that would be considered a multiple degree of freedom system, right? More common, like I said, in structural engineering, is a system like this. Okay, and this is in 2D, right? You could define the location of every one of these points, right? The degrees of freedom on this point in 2D is this point right here can go in this direction, and you can get rotation at that support. You can go this way, and rotation at that point, right? And so this guy has 3 degrees of freedom, 3 degrees of freedom, 3 degrees of freedom, 3 degrees of freedom. And so this would have this would be a 12 degree of freedom system, would be to define what's happening in this frame, right? And you can imagine in 3D systems, right, 3-dimensional systems, right, like in the model you're making in class right now, each one of the nodes in your model is actually a 6 degree of freedom system. You can move it in the X, Y, and Z direction, and you can have rotation around the X, the Y, and the Z axes, right? And so each one of those nodes in your model is a 6 degree of freedom system, right? And then obviously assembling a stiffness matrix for that system is crazy difficult, right? But that's what the computer is doing behind the scenes, right? When you model the whole thing, and part of the finite element analysis procedure is it assembles a stiffness matrix for that whole system, okay? And it's making that, you don't have to go through and do this, right? If you wanted to, you could. You could absolutely do it. You could assemble a stiffness matrix, right? What is K1 and K2 and stuff like that in a big system like that gets complicated. The book kind of steps through for a system like this. What is K1 and what is K2? And there's a 12 EI over L cubed and a 5 EI over L cubed and a PL cubed over 40. All that stuff is kind of built in there, and you could assemble a big matrix for a system that has many degrees of freedom, right? We're gonna leave that to the computers, and we're gonna stick to simple systems like this. But you could assemble a stiffness matrix for this method as well, right? You could also define. So this is the plan view of a building. So if you're looking down on that building, you have like a frame and another frame. You could define the movement of this whole frame with a 3 degree of freedom system. This whole frame can move this direction, it can move this direction, and it can rotate, right? And so this could be considered a 3 degree of freedom system as well, right? I mean, obviously there's, in this frame, there's a whole bunch of degrees of freedom for each part of the frame, but globally you could say, well, what's happening globally with this? Well, globally, it could displace this way, it could displace this way, and you can get a rotation. So this could be considered a 3 degree of freedom system as well. And some people have done this for their projects in the past and modeled it this way. It's kind of neat to see how this works out, right? But study this or just kind of read through that section of the text where it kind of talks about all these different systems and coming up with the equations of motion and what their stiffness matrices would look like and how do you assemble the stiffness matrices, right? But then just keep in mind, we're just doing systems like this, right? Another system that they talk about, it's worth kind of mentioning, we maybe come back to this a little bit later, is that if you had a rigid bar sitting on 2 springs, you could define the movement of this rigid bar in multiple ways. You could define the movement of this rigid bar as a displacement and a rotation, right? That would define the movement of this bar. Or you could define the movement of that bar as a displacement at one end and a displacement at the other end, right? I could define it U1 and U2 being like that. Both methods work, right? As long as you capture the overall perspective, right? You can imagine if I capture what U1 and U2 are doing, that's going to pick up all the rotations and stuff like that. Or I could do this, and then I'll pick up all the rotations and stuff. Either way, this is a 2 degree of freedom system. You can define the movement of this whole thing with just 2 degrees of freedom. And what's interesting about this and why I wanted to point it out is if you formulate it this way, you have an uncoupled mass matrix with a coupled stiffness matrix, right? I mean, this is the coupling again. Coupling again comes from these off diagonal terms. So this is what's happening in 1 degree of freedom is affecting what's happening in the other degree of freedom. And so that's what these off diagonal terms are. So in this case, we have an uncoupled mass matrix and a coupled stiffness matrix. And then over here, if you formulate it this way, your stiffness matrix is actually uncoupled. So you have K1 and K2. So what's happening at U1 does not affect what's happening at U2 because there is no off diagonal terms in your stiffness matrix. Okay. But your mass matrix is coupled, right? And so it's kind of a different formulation of it, right? When we talk about this, we'll come around this a little bit later, but again, one of our modal analysis, what happens when we do a modal analysis is we knock the off diagonal terms off of our equation of motion. And so usually in the system we're talking about, we're going to have a coupled stiffness matrix and we're going to decouple the stiffness matrix, okay? But in some cases, you might have a coupled mass matrix and we have to uncouple our mass matrix in order to solve it. So I just wanted to point that out. Sometimes you could have a coupled mass matrix and an uncoupled stiffness matrix, or and most of the systems that we're going to deal with are going to end up with an uncoupled mass matrix with a coupled stiffness matrix. But just kind of take a look at that. There's all sorts of different ways of thinking about this. Okay, key components here. You have multiples that, a standard frame like you're going to formulate in your code has multiple. You have 6 degrees of freedom per node. And all of those things are part of the whole system. Okay, we're just doing very simple. I think the biggest we get maybe a 4x4, probably I think just a 3x3, where we just look at movement like this, and we're going to deal with like shear frames like this. Okay, free vibration. Kind of set up the basics of this. Hopefully everybody's on par with me. Like I said, we'll do a little review next time we meet in person or via WebEx or whatever it is that we do lecture next. Okay, free vibration. Free vibration is when we have that load P goes to 0. There is no forcing function. So this is, you have a building, right, or a spring mass system. You pull back on it and you let go of it. Okay, and the thing oscillates, right? And it oscillates back and forth between the initial displacements and stuff like that. So this is basically, it's not equal to P, it's equal to the U vector, which is stacked like this. So this is just the same equation of motion before. Uncoupled mass matrix, coupled stiffness matrix is equal to the 0. So this is the same equation they had on the previous page, it's just now it's equal to 0. Okay. Now, what we did when, all right, so this is the equation we're trying to solve. When we did a single degree of freedom system, so just say, I did it in black. Look back to SDOF, a single degree of freedom system. We have a single degree of freedom system. What we did is we had mu double dot plus ku is equal to 0. But then we assumed a solution form, right? We said, well, u is equal to c times e to the I omega t, right? And then so then u double dot just becomes omega squared c e to the I omega t, right? So we assumed a form like this. This is really quick. There's a real quick reminder of what we did, but we assumed a form like this. Take the second derivative of it, and that just omega squared comes out front here. So omega squared c times e to the I omega t. Okay, you took this and you sub it in there. You take this and you sub it in here. So that's what you do. You say this. You go m times omega squared times c e to the I omega t plus k times c times e to the I omega t. Right? So they both are multiplied by c e I omega t. Well, this is equal to 0, I should say, right? So that guy, that's all equal to 0. And so you divide both sides by, well, we'll just pull it out of there. That's what we'll do. So then we go m omega squared oh, did I lose a negative in here somewhere? That's right. Plus k this is a real brief review here. C e to the I omega t. I think I have a negative. I'm missing a negative over here. Missing a negative there, right? So I substitute that in, pull out the e to the c e to the I omega t is all I've done for this next step. That's all I've done between here and here is I just pulled out the c e to the I omega t, pulled it out there. And so in our derivation, we said that this had to happen. In order for you to have a solution to this differential equation with this form of the equation, it has to be true that negative m omega squared plus k is equal to 0, right? And this is where we got omega. This is where we got omega is equal to the square root of k over m, right? Just a review. And you could look back, and like I said, may have made some mistakes in here in this little derivation, but the key point here was in order to solve this differential equation, we assume a form of the differential equation like this. You take the second derivative of it. I think I was missing that negative there. You substitute it in, right? You substitute this in here and this in here, okay? And this is what you get. You pull this component out, and then in order for this to work out, this component has to be equal to 0. This won't be 0, so this has to be equal to 0. And that told us that this omega in this form of the equation up here has to be equal to square root of k over m. And that's where we got the definition of what the circular natural frequency was, or the natural frequency or the natural period of our structure eventually end up being based off of the square root of k over m. Okay. Now when we do the same thing in matrices, let's just remind ourselves what we did here. Now when we do this with matrices, things get a little more complicated, but it's the same idea. That's why I wanted to revisit this, is we're going to come up with something very similar to this. Okay, but in terms of matrices, what does that mean? Okay, so what we do, that's what we're going to do here. All right, so what we're going to do is say, okay, my displacements are going to be, right, they're going to stack up like this. It's going to be a vector. U1 is a function of time and U2 is a function of time. Okay, I'm going to introduce this new thing called phi. That's going to be a vector. And this is the form of the solution I'm going to have. This is the form I'm going to assume it takes. Right, just like I made the assumption with the form of this was going to be, I say that this is what the form of this is going to be. It's going to be this vector times ei to the omega t. Okay, and so what does that look like? Well, phi is going to be a vector. Phi 1, 1 and phi 2, 1. We'll talk about what these are. Right now, just know that there's a vector. It's going to have phi 1, 1 and phi 2, 1. It's going to be stacked like this, and then it's going to be multiplied by this time-changing part. So basically, you just pull this out. The way that scalar multiplication works is these guys can just go out there. That's all this is doing. So I'm saying that the form is going to look like this. It's going to be this phi. It's kind of this. It was just analogous, maybe this c, this constant that's out front. So we have phi 1, 1 times phi 2, 1 times this time-changing part. So I'm going to assume that that's what the form of my u is going to look like. Okay. Then if I take the second derivative of it, right? If I take the second derivative to figure out what the accelerations are of floor 1, floor 2, or mass 1 and mass 2, just take the derivative of this guy. That's the only time-changing part. This is the only time-changing part. So the omega comes out. The i's is where the negative comes from. The two i's multiplied by each other gives you a negative out front. So the second derivative of u gives me negative omega squared times phi times ei to the omega t. So now what I do is I take this guy, take this, right? And I substitute that in. Oh, son of a gun. Oh, that works. Used to be let me do that. I substitute it in right there, and then I take this and I substitute it in right here. Okay. So that's what this is. That's what this next one is. That is what that form of the equation is after I've substituted this in and this in. Okay? And so this is what we get. Okay? It's pretty straightforward there. You can see that they're both multiplied by this same component right here. And so we just pull that out. Okay? So that's all that this is doing, is I've pulled that guy out. There it is on the outside now, and all I'm left with is this on the inside. Okay, and that's equal to 0. Right? In order for this all to be true, that is not 0, and so basically this guy has to be equal to 0. That's what this is right here. That's not 0, so then it has to be that it's equal to 0. Right? In order for that, because this is changing with time, and so in order for this always to be true, this has to be equal to 0. And so that's all that this is shown right here. Okay, I'm just going to rearrange this a little bit, and all I've done in between here and here is I multiply by m to the negative 1, right? So you can't divide by m, right? If I want, I'm just going to simplify this a little bit. Like if this is an algebraic expression, you just divide by m, but you can't divide by an m matrix. If you recall, you have to multiply by the inverse of the matrix. And so what I've done is I've just taken m to the negative 1, m to the negative 1, right? So that's all that this is doing. M to the negative 1, this becomes the identity matrix, which just becomes 1, and so all you're left with is omega squared, and then you still have the negative m to the negative 1 multiplied by that k. So then what we have right here, this is what you would call A classic eigenvalue problem. I don't like eigenvalue, do they? It's a classic eigenvalue problem. Okay. And we're gonna let's dive into that a little bit. So what is it? This is I guess a different way to write a classic eigenvalue problem. This is how it was introduced to me, what an eigenvalue problem was, right? And we're just going to rearrange this in a second, but this and this are the same. Actually, you can see what it is, right? If I just take a minus lambda, right, they're both bolded by x, and so a minus lambda times x is equal to 0, right? That's just rearranging this equation, which is exactly what we have, right? M to the negative 1 times k is the same as a right here minus omega squared. So this and this guy are the same, right? So this, you can see that those are the same things. But the way that I was defined to me, this is how it was introduced to me what an eigenvalue problem is. What this is a matrix. A is a matrix. Okay. It's V, X. What am I doing with this? That is a vector. Okay. And lambda is a scalar. Okay. And so what this is how it was first introduced to me back in the day when I was a math major 20 years ago, is that if I take a matrix, right, A, and I multiply it by a vector, it's the same as if I take a scalar multiplied by that same vector. Okay, what does that mean? Let's say that again. The matrix A multiplied by a vector is the same as taking a scalar and multiplying it by the same vector, right? How we used to use it, like when I first messed around with the eigenvalues and eigenvectors, was for this property right here. Imagine all the steps necessary in order to run this calculation, right? You take all the components of x and you multiply it by all the corresponding components of your matrix, right? And then you add all of these guys up and it gives you the upper left-hand corner of it gives you the upper matrix there. And then you do the same thing. You go to the next one and you take all of these and you multiply them by all of these. And then you go to the next one, you go all these guy, and all these. And so all of the computations needed to carry out a matrix multiplied by a vector. Compare that to multiplying a scalar times a vector, right? A scalar, you just take this times the first one, times the second one, times the third one, times the fourth one. The number of steps you need in order to do this on the right-hand side is significantly less than what it takes to carry out all the calculations for the one on the left, right? This involves all these guys multiplied by each one of these things, and then they get added up, right? So this process is a lot of calculations. This side, not so much. So if you're carrying out a bunch of calculations, if you can simplify some matrix down into this, and you carry this multiplication out a bunch of times as opposed to this one, you save a bunch of time, okay? So that's how we used it. That's how I first used eigenvalues and eigenvectors was by doing this, okay? That's not how they get played out, or that's not how we use them here. Okay, how we're going to use them here is, well, we'll get into that. Okay, so that's what's happening with a classic eigenvalue problem. So this is the same as what's happening here, right? Omega squared. Yeah, so I guess if I take m to the negative 1 times k, right, and I multiply that times the vector, it's the same as if I take this scalar, which is negative omega squared, and multiply it by the same vector. So you can see that that's the same idea here. So in a classic eigenvalue problem, I want to mention some common things here. In this right here, let's just define a couple of terms. In this guy here, I'm going to say that the eigenvalues are lambdas, or what they would call the lambdas in that equation over there. Okay, and then the eigenvectors are what x is, or what the x's are. Let me make that black. Or what their x's are. Okay, lambdas are the lambdas in this equation over here are these are what you would call the eigenvalues, and x's are what they would call the eigenvectors. Okay, both of these. Quit it. Both of these are properties of the matrix A. Okay, which is kind of interesting, right? They aren't just like, right, these things, these, right, in order for this thing to be true, right, or I guess this thing right here, right, it's not just like, you don't just find like, well, it just happened upon an x and it happened upon a lambda that works. They are properties of A. You can calculate for any given, well, certain matrices you can't do it. If they're indeterminate matrices, you can't do it. But anyways, there are certain matrices where you can. For our case, you could do it in all these things. But for any matrix, you can calculate, or sorry, for most matrices out there, you can calculate the eigenvectors and the eigenvalues for that matrix. And there's more than one of them. Okay, they have multiple eigenvalues and multiple eigenvectors. Okay, but they're properties of that matrix. Where do you get them? How do you calculate these things? This is probably what you covered in math class, is how to calculate these things. We're going to let computer calculate these for us. Okay, in particular, MATLAB. Okay. MATLAB is real good at calculating eigenvalues and eigenvectors. Okay, but that's how you do it. The book spends quite a bit of time talking about different methods for calculating your eigenvalues and eigenvectors. That's probably what you did when you covered this in math class. You probably, when you covered this stuff in math class, you probably looked at different ways of calculating what your eigenvalues and eigenvectors are. We're going to let a computer do this for us. There's no need to recreate the wheel. It knows how to calculate eigenvalues and eigenvectors. Okay. We'll say, next thing to mention about it, an n by, how many eigenvalues and eigenvectors do you have? An n by n matrix has n eigenvalues and n corresponding eigenvectors. Okay, so if you have an n by n matrix, it has that many eigenvalues and eigenvectors associated with it. Okay, so a 3 by 3 will have three eigenvalues with 3 corresponding eigenvectors. If you have 4 by 4, you have 4 eigenvalues and 4 corresponding eigenvectors. Okay, and then we should also mention that vectors and values come in pairs, right? They come in pairs, and they have to be used in pairs. And what I mean by they come in pairs means that you'll get a lambda 1, and that corresponds to an x1. You'll have a lambda 2, and that corresponds, straight. I'm going to do it this way here. Lambda 1, x1 vector, lambda 2 corresponds to x2 vector, etc. Dot, dot, dot. They come in pairs. That's also an important thing to note. You can't mix and match them either. They only work together, right? They only work together. Okay, so that's eigenvalues in general. Like I said before, I'm going to give myself a little bit of room. I'm going to move all this stuff down just a little bit. Crowded. That's just the classic eigenvalue problem. Let's come back to this now, right? Come back to this system right here. Right, in our system, it's the same, right? We just showed that it was the same. In our system, though, I'm going to take this. That's our system right there. And we'll take this. So our matrix that we're talking about is m to the negative 1. Right? Well, that's the inverse of the matrix, right? You don't just take the inverse of individual components. That's the inverse of a matrix, okay? Which you guys learned about how to do it. MATLAB's going to do that for us when we get there. Okay, you take that and you multiply it by the stiffness. That is a matrix, okay? That matrix right there is going to have properties, right? And it's going to have mode shapes. It's going to have vectors. Right? Phi is what our vectors are going to be. These are going to be our eigenvectors. Right? We're going to ask MATLAB, we're going to say, hey, here's my matrix, m to the negative 1 times k, and it's going to give us a bunch of phis. Those phis are what our eigenvectors are going to be. And then the omega squareds are going to be the eigenvalues. Okay, and what these are going to be, these eigenvectors. I'm going to type those. Yeah, I'm going to type those. It's important here, so I want to make sure that we got it. Eigenvectors. These are going to be what we're going to call the mode shapes. These are going to be our eigenvalues, which are going to be our circular natural frequencies. Same as or similar to what we found for MDOFs. In this case, one more comment here. MDOFs. Number of degrees of freedom equals number of mode shapes. Okay. There's a lot here. There's a lot going on here. Okay, so let's just take a step back. We just talked about these eigenvalues and eigenvectors. Really neat concept, right? It's what's happening. Right? It's this right here. So if you take a matrix multiplied by a vector, it's the same as a scalar multiplied by the same vector. Right? That's what this is right here. When we went through this derivation, right? Well, why do we even visit this? Well, we visited it because when we assume a form of a solution to our multiple degree of freedom system matrix that we have here. We assume what it looks like, the form of the solution looks like. You take that, you substitute it into your differential equation, your multiple degree of freedom differential equation, and leads us down. And in order for this to work, in order to solve this, to come up with a solution of U1 and U2, because that's what we're after, we're looking for what is the displacement of mass 1 doing. That's what we're trying to solve. Don't lose track of all that. We're trying to figure out what is U2 doing and what is U1 doing as a function of time, and how do they affect each other. Right? We're trying to solve that differential. In order for that whole thing to work, this has to be true. It was very analogous to omega had to be square root of k over m. We have to solve this eigenvalue problem in order for us to be able to find what U1 is doing and what U2 is doing. Okay, that eigenvalue problem manifests itself like this, okay, where this is the matrix, and that's the matrix, and it has certain elements, right? It has vectors and scalars that go together in such a way as to make this whole statement true every time. Okay, or another way to think of it is you can ask MATLAB for the eigenvalues and eigenvectors, and it will return to you a bunch of omegas and a bunch of phis such that this works. Such that if I take that matrix and I multiply it by this vector, it's the same as taking this scalar and multiplying it by that vector. Okay? Hard to, right? So like, what the hell? So, okay, we kind of got an idea of like how or what, maybe a little bit how we ended up here. Okay? And so that's what we're going to end up doing, is we're going to say, hey, look, MATLAB, tell me what the eigenvalues and eigenvectors are of m to the negative 1 times k, right? This will just give us one big matrix, okay? And what it'll return to us is phi. It'll return to us however many degrees of freedom. It'll give us a bunch of phis and a bunch of omega squareds. If it's a 2 by 2, it's going to give us 2 mode shapes and 2 omega squareds. This will be the mode shape, and that'll be the frequency of the time changing part, which we'll get into it. Okay. And you need these things in order to solve the whole system. Okay. In order to solve that system, you need phis and you need those omegas. You need those eigenvalues and eigenvectors. Otherwise, the whole system doesn't work. Okay. It's very similar to omega had to be equal to square root of k over m. You had to have a natural frequency. Okay. Now, this is why I was pausing earlier, because there's a lot going on. I want to hear from you right now. I want to hear, what do you think? What are some questions you have? Maybe start building up your questions when you watch this. Like, what the hell are you even talking about, right? Do that. And we'll talk about it next time we meet. Okay. So, once you do that, and we'll get back to this. I want to show you a little animation here in a second, but to kind of help with this. And so once you work out what those phis are, right? We haven't gone through the whole solution procedure or anything yet, but one of the steps when we go through the procedure is we're going to have to calculate what our mode shapes are and what our frequencies are. Okay. But once you get those things, your overall answer is going to end up looking like what I have here. Your overall answer, right? What we're after is the displacement of each of the floors, right? And what the overall answer is going to be what our mode shape 1 is multiplied. This is a time changing part. So eventually we're going to get to this, what this ends up being. But this is going to be what we call Q as a function of time, right? So you're going to have a certain shape. The total answer is going to be a certain shape. Phi1 is going to be a certain shape. It's going to be the primary mode of it's the primary eigenvector of this vector right here, but it's going to be a certain shape. That's going to be a shape multiplied by a time-changing part that has a frequency which is the same, which we get from the eigenvalues of this matrix. Okay, and so it's going to have an oscillation. It's going to oscillate with omega 1, and it's going to have a shape of phi1, right? And that's just part of it. Okay. And so this would be considered what mode 1 is doing. Mode 2 is doing this. It's going to have this shape. It's going to have the shape what feed 2 is, and then it's going to be oscillating with a frequency of omega 2. And then you're going to go all the way up to the mode whatever, and it's going to be oscillating at a frequency at whatever mode that is, okay? This omega comes from the eigenvalues of this matrix right here. And then the phi, the shape, is the corresponding eigenvector that comes from that matrix as well, okay? Like I said, that's pretty deep. It's jumping ahead, but the key components there are the displacements of each floor are going to be captured by this guy. Right? This is going to have a certain shape, and that's going to have the different floors. And this is going to be the time-changing part. So we've got the shape and a time-changing part. Okay. So let's see just conceptually what's happening with this. And this is we're going to have to beat this guy. We're going to have to beat this horse to death in order to get this one through, because there's a lot going on. Okay. So here's a quick little example. Right? I'm going to skip all sorts of steps in the process. Okay. But just kind of seeing how this plays out. So here's a system right here. Okay, we've got a stiffness of 2K in the bottom and a stiffness on the second floor of K. We have 2M for the mass on the first floor and M for the mass on the second floor. So this is a 2 degree of freedom system because we're treating these guys as shear frames. Those are shear frames. And so this guy's got a mass. In this example over here, M is equal to 10 and K is equal to 1,000. And so if I assemble my stiffness matrix, right, sub everything in there, we got negative, that's what our stiffness matrix looks like, and our mass matrix looks like this. Okay, so then what I did is I went to MATLAB. I set up this whole thing in MATLAB, right? Then I went to MATLAB and I said, hey, MATLAB, give me, and we'll get to this a little bit later, but the command is eig m to the -1 times k. Right, that's a matrix. And then what it returns to me, and again, the syntax, so we got to cover the syntax. There's a lot going on there. But I do that, and what it returns to me is this guy and this guy. Okay? And then what it tells me is that my phi, my mode 1, is 0.5 and 1. Okay? And then its corresponding omega squared, which is, so this is the eigenvector, and then this is the eigenvalue, is 50. So MATLAB returns to me 0.5 and 1 and 50. Okay, that's mode 1. It also returns to me, again, syntax is something different, but it also returns to me -1 and 1 and 200. Okay, so this mode shape has a frequency of 50. Okay, a frequency squared of 50. And then this mode shape has a frequency of omega 2 squared of 200. Okay, and then from that omega, you can calculate what the t is as well, because it's just 2 pi over that omega. Okay, so this would be 2 pi over omega 1, and this would be 2 pi over omega 2. Right, you have to do the square, which is the square root. Right, this is the omega 1 is the square root of 50. Right? But anyways, so this is what my period is. T1 is 0.89 and T2 is 0.44. Okay, so what does this mean? Okay, so that's what it returns to us, is that it's going to look like that. Right? So what does this mean? What does it mean to have a mode shape that looks like this? So what you do, right, this is the book's quick little solution of it, is you plot these things. Okay, so this is 0.5 at the first floor and 1 at the second floor. So what that is right here, this is 0.5, and this right here is 1. So that's what that mode shape looks like. That mode shape, 0.5 and 1. Okay. The second mode shape is -1 and 1. So this one right here, right there, would be -1. And that one right there is 1. So that's what that shape looks like. So you kind of just plot that shape. So there's what here. And then the reason it kind of curves is because the way a shear frame works, right, is it comes out with no displacement, and then it comes up, and then no rotation and no displacement. Then it comes up and has no rotation, and then it comes back, and then it has no rotation, because this is infinitely stiff up at the top, and so it can't have rotation. Same thing with here. That's why it comes out like that, and it's perfectly vertical is because we're assuming that that's a rigid frame. That's why they draw those looking like that. Right, so this mode shape would be, that's what mode shape 2 would look like. Okay, because it's only a 2 degree of freedom system. Okay, and so if we're looking at the overall, the oscillations back and forth, we say that it's going to oscillate with a T1 of 0.89, right? Which comes from its eigenvalues. And so what happens is, remember we came back up here and we said that this is a time changing part. Q is a function of time, right? And so this is oscillating, right? This oscillates. It's hard to see ei to the omega 1t. It's hard to see that this oscillates, right? When we write it in sines and cosines, a little bit later we're going to write that in sines and cosines, but really this is an oscillation, right? All these are oscillations where these things and they're rotate, or they're oscillating at these frequencies, omega 1 and omega 2. So in this case right here, this is what Q is a function of time. Like I said, this is going to be, this ends up being a cosine curve as a function of time. This period right here, right there, that period right there would be 0.89 in our example. Right? That's how long that would be. Okay, and so this is like I said before, I said that this was the Q part. This was the time changing part. That's going up, that's the oscillation. So here's Q over here. And so what this is, my overall response for mode 1 is going to be that shape multiplied by Q, right? So right at t equals 0, my Q is equal to 1. And so right at t equals 0, it's going to look just like that, okay? At a little bit further, at B, right, just a little bit more time, it's going to be reduced a little bit. And so my answer is going to be this original shape, but instead of multiplied by 1, it gets multiplied by slightly less than 1, right? It gets multiplied by whatever value is right here. And so that's what it looks like there, okay? Then once it gets out to point C right here, a few seconds later, it's multiplied by 0. So it's this original shape multiplied by 0, and so it looks like that. It's going to be straight up and down because it's that shape multiplied by 0. Then you come over here to D, and that's right there. So it's a negative value, and so there's D right there. So it's the original shape multiplied by D. And then E is negative 1, and it's right here. Oh, sorry, negative 1 is right here. It's negative 1 multiplied by that original shape. There it is right there. And so what does this say? This says this thing starts out like this, and then it oscillates, and it just rotates, or I guess it just kind of sways back and forth, okay? And the frequency of that is defined by what we got as our first, and ultimately came from what our first natural frequency was from our eigenvector, okay? And so again, coming back up to here, our total response is going to be that mode shape multiplied by the time changing part. There's the mode shape multiplied by the time changing part. The total response is going to be this guy plus what's happening at the next mode, right? Because it's saying it's this one plus this one. Well, what's happening at the next one? Well, it's the second mode shape multiplied by its time changing part, which is oscillating with omega 2. And so we come over to this guy. There's the mode shape over here and then over here, okay? Same idea. It's that shape that gets multiplied by this Q, right? Now this distance right here in our example above there is 0.44, right? So this one oscillates faster. This one's slower, and this one's oscillating faster. It happens more often, okay? And so it starts out with that shape, then it multiplies it by, same idea here, by B, so it's a little bit less than 1. So then it gets then this is what it is at a shortly different time, okay? When this thing's equal to 0, right there, then this thing is just straight up and down. Then when it's equal to the negative value, then it's this guy. When it's equal to negative 1, then it's this guy, okay? So this one, just kind of an overall drift that way, then drift this way. This one is kind of a wiggle, right? It goes like this, it rotates to that one, then it goes like this, and you pick up what they call a node, okay? And so there's a certain spot that doesn't move, okay? And we'll cover those a little bit later, okay? There's a lot to take, right? There's a lot going on in this lecture. You can see why I hesitate to just like give this and watch this, okay? But there's a lot going on, right? And so the total response is going to be this guy going back and forth and this guy wiggling, right? And so where did this shape come from, right? This shape came from it's the first eigenvalue and eigenvector pair. And this is the second eigenvalue and second eigenvector pair, okay? And that's assuming they get sorted out with these guys starting out smaller and getting bigger. Okay, and that's usually how the MATLAB usually returns it. It returns to the smallest frequency to the largest frequency. Right, we haven't talked about what Q is going to be. Right, we'll cover that a little bit later. Right now, we're just introducing this concept of there's going to be a time-changing part multiplied by a mode shape. Time-changing part multiplied by a mode shape. Okay, so I actually have an animation to show you here, and we'll call it after this. But here's an animation of a 3-story building. Okay, this 3-story building, it has basically 3 different displacements. I've kind of pulled it back to here, pulled this one back to here, and pulled this one back to, pulled this one back over here, here, and here. So that's its initial displacements. And when you release this thing, you can imagine that this one's pulled back more than the other one. So this one's going to like whip forward, which is going to kind of pull the second floor this direction. And then this floor will be affecting what's happening with this floor. And there's going to be, it's a real complicated procedure, right? Because they're all coupled by the stiffnesses on the different floors. And so you're going to have this thing, this is going to whip forward and it's going to pull this, and then this is going to pull the bottom one, but then this one's going to whip back, and then it's going to move this one, which is going to move this one, and it's a really complicated process of what's happening when everything is wiggling around, right? But the whole idea when you do this modal analysis is I can decompose that motion into what's happening. So this is what mode 1 is doing. Right, so I assembled a big stiffness matrix for this big whole thing, and then it's actually only a 3-degree of freedom system, right? It's just 4, 1, 4, 2, and 4, 3. But I assembled a stiffness matrix associated with that, and I said m to the negative 1, what are your eigenvectors? Here's the 3 eigenvectors. It gave me this shape. This is mode 2, right? And then mode 3 was like this. Okay, and so it gave me, this one's all 3 to the right, this one's 1 to the left, 1, 0, and 1 to the right, this one's left, right, left. And so those are the mode shapes, mode 1, mode 2, and mode 3. The other thing it returns to me is these frequencies. That's the frequency, or that's the period of mode 1, that's the period of mode 2, and that's the period of mode 3. And you can see that period decreases as it goes up, or the frequency increases as you go up. Okay, so this one's going to oscillate at a slower speed, this one's going to oscillate at a faster speed, and this is going to oscillate even more, okay? And then you can see that, and then the total response is going to be this guy, plus this guy, plus this guy, all of them added together. And you can see that and you'll be able to see each of these modes in this response over here. This is going to be just a rocking back and forth, a slow rocking back and forth. This is going to be a wiggle, and it's going to be even more of a wiggle. Okay, so let me see if I can get that animation to work here. Oh, I just had it. I messed up. Oh, where did I put that? MATLAB Drive. 512, there it is. Right. So it's kind of hard for me to point once it's doing this oscillation stuff, but here's the overall response. You can see that it's a pretty complicated wiggle, right? There's, again, what's happening on the first floor is affecting what's happening on the second floor, what's happening on the third, and so forth. Okay, but that motion can be decomposed, or where it actually is coming from is mode 1. So this is mode 1, right? Mode 1 is just the oscillation back and forth with the original mode shape. It has a natural period that's bigger, right? You can see that it's slower. I guess another way to look at it. Okay, and then you have this guy right here, which is the mode shape 2. You can see that the second floor is not moving because the mode shape in that case had a 0 for the second floor. Okay, and it's got one little wiggle associated with it, and it's at a slightly higher frequency, okay, or lower period, you can think of it. And then the mode shape 3 is what you see on the far right over here. Okay, and it's even more of a wiggle, but it has a smaller period or a higher frequency. Okay, and the overall response are those three added together. This guy plus this guy plus this guy. And you can see them in there. They're all there. You could definitely see the slow rocking back and forth. Okay, you can see the other wiggles are kind of mixed together, but they're all in there. I mean, that's how we're going to solve this thing, is we're going to break this thing down into its different modes and then add up all the solutions. Okay, fundamentally what's happening, we haven't covered that yet. We just kind of I just want to get a feel for how this whole process works at this point. It works by breaking it into different modes and its different frequencies, and then bringing up those modes are the eigenvectors of your matrix m to the negative 1 times k, and the frequencies are associated with the eigenvalues. The frequency, the circular natural frequency squared, are the eigenvectors or eigenvalues associated with m to the negative 1 times k. Okay, so stare at this a little bit more. Beautiful, beautiful MATLAB skills here in order to demonstrate that to you. Okay, good luck. Save up all your questions. I know there's going to be a bunch of them.